Hello, I'm Nathan Musoke from the University of Auckland, and I will be talking about the nonlinear evolution of inflaton perturbations during the Primordial Dark Age. This is work I did with Sean Hotchkiss and Richard Easter, also at the University of Auckland. I'll just give a brief outline of what I'll talk about. I'll start by just doing a brief overview of inflation and then reheating, and then I'll talk about a code we wrote to analyze a particular phase of reheating, then show some results and a conclusion. So as most of you know, primordial inflation has been proposed to solve some of the initial conditions problems in the early universe. So this early phase of exponential growth would explain the observed flatness and homogeneity of the present-day universe. So we expect that there have been at least 60 factors of 10 of expansion since the beginning of inflation, maybe more. Of those, 30 took place during inflation, another 15 after inflation, before Big Bang nucleosynthesis, and then the last 15 factors of 10, containing everything else from formations of galaxy to the emergence of life, are just a quarter of the total expansion history in a logarithmic sense. And the reheating phase comprises another whole quarter, but we don't know much about it. So reheating explains how we make this transition from inflation to Big Bang nucleosynthesis. So as I said, we've got a universe nearly full of this homogeneous inflaton condensate at the end of inflation, and somehow Big Bang nucleosynthesis needs to happen. And the processes which take place in the intervening time can have effects on the predictions of a model of inflation. So it could be the general viability if there's no way for the inflaton to convert to the precursors for the Big Bang nucleosynthesis, then the model's not going to work at all. The speed at which reheating takes place, if it does, will tell you the amount of inflation which is required. So the number of e-folds of expansion you need. And if there's some sort of coupling between the inflaton field and dark matter fields during this phase, you can also get predictions from there. So there have been a few scenarios examined. In the early days of inflation, people, of course, realized this reheating had to happen and found that if there were self-interactions of the inflaton field or couplings to other fields, then you can get resonance at preheating, and the inflaton field fragments very quickly. That initial homogeneous condensate doesn't last very long. However, if couplings are very weak, then reheating happens quite slowly. The inflaton field can oscillate in the bottom of a minimum without having large perturbations form. So there's been some work on that. About 10 years ago, it was found that the perturbations in that inflaton field without couplings grow gravitationally, and they grow about linearly with the scale factor. And that the scales with the most growth are those on the horizon at the end of inflation. However, those analytical techniques were not able to go into the nonlinear regime and find the end state of that collapse. So this is research which just published in PRL this year, which has gone and examined that nonlinear collapse. So in our scenario, we assume that we just see the last bit of oscillation in the bottom of the inflaton field, inflaton's potential after inflation ends. And we assume that the field has a potential of m squared phi squared. So as I said, the inflaton has coherent oscillations around the bottom of that potential. Those take place with the characteristic time scale of the mass of the inflaton field. And as I said earlier, the density grows with the scale factor. So these two processes happen on quite different times. The Hubble time and the oscillation time have a ratio which is proportional to a to the 3 halves. And if it takes quite a long time for the field to become nonlinear, this a to the 3 halves can become quite large, and you have a large number of oscillations happening before the field becomes nonlinear. So the inflaton field obeys the Klein-Gordon and Einstein equations, Klein-Gordon describing the scalar field dynamics, and the Einstein equations coupling it to gravity. So just trying to solve those directly, because there are a huge number of oscillations late in the evolution, it becomes very difficult. However, we found that you can make a transformation and turn the Klein-Gordon equations into the Schrödinger-Poisson equations. So making a substitution of the inflaton field to a new field, the exponential term factors out the oscillations in the field, and you get the Schrödinger equation, which is the usual that you expect, where the potential is the gravitational potential, and the gravitational potential is solved through the Poisson equations, which are sourced by the square of the inflaton field, which is dimensions of mass. There are some limitations to this approach. The largest scales have to be subhorizon, which is okay for us because the scales which we expect of the most interesting physics are on the horizon at the end of inflation. The horizon then grows and they become inside the horizon. The field has those small derivatives, both in time and in space, and expansion shouldn't be too fast. And all of these criteria are satisfied just a little bit after the end of inflation. So we adapted the code PyUltraLight, which was written for ultralight dark matter, and called it PyUltraDark because we're using it in the primordial dark age. We added in expansion, adaptive time steps, cosmological initial conditions, and consistency checks on the phase. So we have to check that the gradient of the phase of the field does not change by more than pi from cell to cell on the grid, because that is associated with the velocity, which means that we can't handle large velocities, and of course we can't handle the formation of black holes and other extremely compact objects. But if we found that that was happening, then we've already got a result anyway. So we did some checks that the code agrees with perturbation theory. On the left, you can see a field as predicted from simulation and from theory. By eye, they look okay, pretty similar. Looking at the relative error, after having expanded by a factor of 10 to the 3, they have a maximal error of on the order of 1%. And this is just looking at the same simulation, but the spectrum. So starting with a flat spectrum and evolving it forward. The blue is the simulation, and the dashed orange is perturbation. Again, they line up well. Smaller scales, there are some deviations, especially past the cutoff in the initial conditions. And then you can see that the root mean square of the density contrast delta matches well as well. And you can see a further feature that it initially oscillates and then starts to grow when the wave number of the modes in the box becomes of order the wave number of the horizon. Right, so these are the results of the simulations we were interested in doing for the early universe. We started the simulations after the universe is expanded by a factor of 25 after the end of inflation. So that's the blue dash curve, and evolve forward another factor of 10 to the green curve. You can see that there's an orange dashed line as well. That is the perturbation theory prediction at the time of the green curve, and you can see that they deviate, which we expect because we are going nonlinear, but that confirms that perturbation theory doesn't work there. The initial spectrum has a cutoff at the size of the horizon, but then there's nonlinear coupling, which makes those modes grow in the simulation. We also looked at the maximum density contrast across the box, and you can see that the density contrast becomes of order hundreds at some place in the box. So that's extremely nonlinear. And again, for perturbation theory, that isn't the case. And even the root mean square of the density contrast grows quite significantly. So this is a slice through the final box in the plane containing the point with the largest density contrast. At this point here, and you can see hints of some sort of web-like structure, which is not surprising, since the Schrödinger-Poisson equations can also describe the formation of structure in the late universe in ultralight dark matter. It's not surprising that we can see a similar phenomenon in the early universe. And it really shows the parallel between the two phases. Now in the bottom, I've shown the gradient of the phase. As I said earlier, that is related to the velocities of points of the field on the box. And you can see that this point with the largest density also has points surrounding it with a large phase gradient. So those will be places where there's a large velocity of things infalling to that large overdensity. And again, for this overdensity here, you can see a similar effect. And then we also did a pretty picture volume rendering of the final box. And again, you can see little overdensities all over the place, and what looks like a web-like structure connecting. So we showed that the post-inflation dynamics of the inflaton are described by the Schrödinger-Poisson equations. And we can simulate the gravitational growth of perturbations in the inflaton field during reheating. And this hasn't been done before. There are analytical calculations showing that it starts and it should happen, but we haven't seen the nonlinear growth before. And we've confirmed that nonlinear structures form in this very early phase of the universe, and it's analogous to structure formation in the late universe. We haven't made concrete predictions for how this changes in the observables of inflation. That will require more advanced codes to go further and make observational predictions. Yes, so thank you for your time, and I look forward to hearing what questions you have.